Hello, welcome back to another episode of Math with Haas. So, in the previous episode, we introduced the logarithm as the inverse of the exponential function. Now, we need to make a couple clarifications about the logarithm. So, we have y equals log base b of x. Now, the domain of x, or of our log here, x must be a positive number. You cannot plug in a negative number, and you cannot plug in 0. The reason why is because when we think about this function y equals b to the x, there is no way that y can equal 0 or a negative number. Actually, we should just write y cannot. It's impossible for y to be less than or equal to 0. So y, you cannot, doesn't matter what you plug in for x, positive, negative, 0, you cannot get y, the output, to be 0 or negative. And so this here will become a domain restriction for our logarithm. Furthermore, we must specify that our b value for the log, so b must be greater than 0. Well, we should just say b must be greater than 0 and not equal to 1. So we're going to restrict b to positive values and not equal to 1, simply because if you think of 1 to the 5th, well, that's just 1. In fact, 1 to anything is just 1, which is why we're going to exclude b equals 1, and we're going to exclude 0 and negative numbers as well. Alright. So with that, let's see. So with that, we will continue on. Now you might be wondering, what about the range? So the range of the logarithm is going to be all real numbers. In fact, I'm going to use this notation here. This funny R means all real numbers. So we showed in the last video that you can plug in a value into a log and get out 0, but how would you get out a negative number? That seems strange. Well, that'll be one of our questions we look at today. So if we use our properties, let's go ahead and do some examples. We can simplify some expressions using our properties. If we recall, our properties are, we have log base b of b to the x is equal to x, and we don't want to use an a, we want to use a b. And we have b to the log base b of x is equal to x. We have these other two, which we could think of as a property, where if you plug a 1 into a log, you get out 0. If you plug in a value that's the same as the base, you get out 1. So those are our properties that we prove. So let's see here. If we have, let's see here, log base 3 of 27, what does that equal? Well, if we think about the number 27, it's divisible by 3. If you didn't know that, one way of determining whether a number is divisible is if you just add up all the digits, and if that gives you a number divisible by 3, then you know this number is divisible by 3. So if we think about 27, it's actually, well, if you divide out to 3, it's 3 times 9. Well, 9 is just 3 times 3. So we could think of this log as 3, log base 3 of 3 to the 3rd. Now, if we think about our properties here, we have a situation like right here. You have the base being the same here, so the exponential base is the same as the logarithm base. So the output is just going to be the exponent. 3. If we have, say, log of 1000, well, remember, this log here is the common log, so that's log base 10. And similarly, 1000 is 10 cubed, so we get out 3. If we have, say, 2 to the log base 2 of, how about pi, because it's delicious, well then this one would be our second property up here, right? So log base 2, well 2 log base 2 of pi is just going to be pi. The exponential and the log cancel each other out. Now, we can also, if I plug in, how about log base 81 of 1? Well, doesn't matter what the base of the log is. If you plug a 1 in, you get out 0. Another example will be, how about log of log base 900 of 900? That will also be a 1, because the base here, the log space, would match the input. So 1. Or you think the exponent here is just a 1 and you think of it in terms of the first property. So there are some examples of simplifying some log expressions. And they all just immediately follow from the properties. Now, here's a new question. What if we have log base b of a to the c? So notice what's inside our log is an exponential, but it has a different base than our logarithm. So let's go ahead and think about this. So if we have log base, that's a terrible O. So if we have log base b of a, we know that this is equal to a, right? So if I raise both of these to the c power, so to the c to the c, then I have a to the c on the right. In fact, we'll call this a proof, even though we don't even know what this is yet. And then on the left here, this is the same thing as b to the log base b of a, and we'll have a c in front because of our properties of exponents. When you have something raised to an exponent, let's say to the y, and that's raised to the z, that's the same thing as x to the yz power. So this is the property of exponents we are using. So this is what we have here. Now, if we were to take the log of both sides, so if I were to say log base b of b to the c log base b of a, well, that what you do to one side you have to do to the other, so I have to take the log of this side as well. Alright, now if we are careful, we can notice that the base of the exponential and the log are the same, so we can use our log property and we can think of all of that being canceled out, so go away. That leaves us with c log base b of a is equal to log base b of a to the c. And that's our proof, or derivation, however you want to think about it. So what this says is, if I plug in an exponential into a logarithm, the exponent you can move out as a coefficient. So our exponent here can move out and you can just multiply it by the log. It's a very useful property and it will be made use of a lot. So c log base b of a. And this is our first law of logs. Alright, we'll put a box around that. That's one of our important fun facts about logarithms. Alright, now you might wonder about this question here. If we have, suppose we were given this, log base 2 of 10. How would we plug that into the calculator? If we had, say, log of 20, well, we can plug that into the calculator because we have a built-in button right here. Log of 20, boom, 1.3, etc., etc. Similarly, if we had we have natural log, so we can just plug that in. Natural log of 20. So we have those buttons there. That's almost 3. But what about natural log or log base 2 of 10? Well, some calculators like this one, you do have a function somewhere in here. So I hit math, and then now we just scroll down, see if we can find that relevant. Oh, here we go. So we hit enter here. So log base 2 of 10, and it does it for you. But what if you don't have a fancy calculator like I do here? What would you do next? Well, what we need is to figure out a way of converting our log bases. If we can figure out a way of converting our log base into something that our calculator can use, then that would be very useful for us, and it would also be useful for solving some of our problems. So the answer to this problem, is going to be the change of base formula. So the change of base formula says this: if I have log base b of something, that will equal log base, how about c of a over log base c of b. So if I want to change the base here, what I need to do is pick a new value for c. Usually it's either Euler's number for the natural log or 10 for the log. And then what I originally plug into the log will go inside the numerator log, and then the old base goes into the denominator. So now let's go ahead and prove this. That way it doesn't appear as a mysterious fact out of thin air. Alright, so let's think of this. So if we have log base b of a, that's going to equal x. Okay. Well, we can rewrite this as an exponential, so b to the x is equal to a. Alright. And we can take the log of both sides here. So if we say log base c of b to the x, that has to equal log base c of a. Okay. Now, let's see here. If we think about our left-hand side here, we can notice that we can use our new law of logs that we derived. So that is x log base c of b is equal to log base c of a. I'm going to go ahead and get x by itself, so I'm going to divide out this log expression. I'm going to have to do that to both sides. What you do to one side, you have to do to the other. So now I have x is equal to log base c of a over log base c of b. Now, at this point you might be wondering, okay, but what about this x thing? What are we supposed to do with that? Well, if we remember that x is equal to this expression right here, we can just substitute that in, and then we have log base b of a is equal to log base c of a over log base c of b, and that proves our change of base formula. So what this says then, if I have something like log base 2 of 10, well, this is really the same thing as if I'm going to pick C as 10, so the common log. It's the same thing as log of 10 over log of 2. So let's find out. So log of 10 divided by log of 2. And we can confirm that it is the same. Okay. So using the pre-built compute function in the calculator, we get the same value as our change of base formula. So this will be super useful for those of you who do science, chemistry, and all that. You got a bunch of logarithms. Change of base formula shows you how to change that from one base to another. Now, these laws and properties, they do also apply to the natural log. Some of you might have been wondering, well, what about natural log? So I could have easily have picked log base 2 of 10. That will equal the natural log of 10 over the natural log of 2. Let's see here. So natural log of 10 divided by natural log of 2. Same value. So it really doesn't matter what you pick for your base. However, you should pick 10 or E, Euler's number, or the common not. So the natural log or the common log, simply because those are built-in calculator functions. So one thing I do also want to say is the natural log, it does follow all those properties of log. So if you have like natural log of how about e squared, that would equal 2, because natural log is, you can think of it as log base e of e squared, and so that property would cancel them out. Though you definitely don't want to be thinking that, you want to think as natural log and not log base e, because that's bad notation, but this is what's really going on. Similarly, if you have e to the natural log of, I don't know, how about pineapple? Then the e and the natural log will cancel each other out, leaving you with just pineapple. I mean, it doesn't really matter what's inside. What matters is identifying the fact that the natural log and the exponential, since they are the same base, they kill each other off, leaving you with just pineapple, which is delicious. Alright. Now, at this point, I want to say thank you for watching this video. If you've been enjoying our content, please subscribe, check out our Patreon page, and support us. And thank you for joining our math party. We'll see you next time.